Hello, Algebra 2 classes. Welcome to the review lessons. So since we don't have final exams this year, what I can do is I can focus on what I think are the most important topics for next year. Because if we had finals, we kind of have to review everything. But as I've mentioned during the year, some topics are going to be more important. You're going to see them more often next year than some other topics. So I've selected 5 topics, and I'm going to do 5 review lessons on those topics. So here's the first one. As you go into Precalc Enrich next year, you need to remember their transformations. Now, that doesn't mean when you walk in day one, you remember everything, but you need to know these well enough that as soon as they come back in next year while you're in Precalc, that you're able to do the work. So the transformations, if we have a function, f of x, we know that if we add or subtract numbers inside with the x, that's going to make certain changes to the graph. If we add or subtract numbers outside, that's going to make certain changes to the graph, and multiplying by a constant out front can make other changes. So if we add or subtract a number outside, that's going to be your vertical shift, and that one works the way you want it to. If you see plus a number, it moves up. If you see minus a number, it moves down. This minus c inside is going to be your horizontal shift. That's going to move your graph left and right. And that works the opposite of what you expect. That's why that minus is there. So if you see a plus, you move to the left. If you see a minus, you move to the right. And then the a out front controls a few things. If a is negative, then there's been a reflection over the x-axis or a flip over the x-axis. The other thing a controls is vertical stretching and vertical shrinking. So if we have a number out front that we're multiplying by whose absolute value is larger than 1, so if you put like a 2 out front, or you put a 5, or you put a 3/2, or even if it's negative, it can still be a vertical stretch. So if the absolute value of the number you're multiplying by out front is bigger than 1, it's a vertical stretch. And if you multiply out front by a fraction, so a number that's between 0 and 1, whether it's positive or negative, that's going to cause a vertical shrink. And let's review some examples now. We're going to start off with some general functions. So these are not special graphs that I know the equation of. I just made these up. So this is function f. And what we want to do is practice transformations by graphing f of x minus 1 plus 2. So the minus 1 inside is going to be a horizontal shift. That works the opposite of what you expect. That's going to move us right 1. And then the number that's being added outside represents a vertical shift. Since it's plus, that's going to move us up 2. So you could move everybody right 1 and then move everybody up 2, but you guys were comfortable when we were reviewing this just to move 1 to the right and up 2. Kind of do both transformations at once. So I'm going to take this next point that stands out here and move it 1 to the right and up 2. And I'm going to take this end point and move it 1 to the right and up 2. And then if I connect the dots, I should have kind of like a parallel graph. It should have the same shape. It should just look like I just moved it. Okay, and that's what I was going for there. So that's our first example. Here's our next example. I made this one up. I just made up a graph. I decided to give it 3 distinct points connected by those segments. And what we want to do is we want to reflect over the x-axis. So to reflect over the x-axis, we can count the number of units away from the x-axis. So if we look at this end point here, see it's 2 units below the x-axis. Its mirror image would be 2 units above the x-axis. And we technically want to do that with all the points on the entire graph, but we don't have to do that with every single point on the entire graph. If we move these 3 special points that have been accentuated, then we can connect the dots and we'll be good. So let's focus on this point next. If we want to reflect over the x-axis, this is 2 units above. So when we reflect over the x-axis, it goes 2 units below. And then this is 1 unit below the x-axis. So its mirror image is 1 unit above. And when you connect those dots, you might notice what should happen here is the point that's on the x-axis from the original graph, you should cross right through that. Because if you see this point, think of that point on the original graph right there. Since that's on the x-axis, when you flip over the x-axis, it stays right where it is. So that should be your graph. It should look like a mirror image of the original. I have two more of these for us to try. They're not always called F. They can be called G or H, like over here. And this one here is going to be a vertical stretch by 2. So that's going to make our graph steeper. The way that we handled vertical stretches when we reviewed this year was we looked at the ordered pairs and we said we're going to keep the x's the same and multiply the y's by 2. So some of you like to list the ordered pairs right on the graph. And some of you like to make a table over here on the side. And some of you were able just to look at the y's and multiply by the appropriate number. So let me start with that way, and then I'll show some work for anyone who would like work. So looking at this point right here, the y coordinate is 3. So if my vertical stretch is by 2, when I multiply that by 2, I get 6. So I'm not moving this up 3. It's not a vertical shift. What's happened here is the y coordinate was 2, and I multiplied that by 3 to get 6 for that y coordinate. Here, the y coordinate is 0. When I multiply the y coordinate by 2, it stays where it is because 0 times 2 is 0. Here, the y coordinate is -3. When I multiply that by 2, it moves to -6. Here, the y coordinate is -2. That's going to move to -4. And when we connect the dots, what should happen is we should have a graph that looks similar to the original, but it looks steeper. It should actually look like you pulled it away from the x-axis. So you pulled this point up and you pulled these points down, and this point stayed where it was because the y coordinate there was 0. So if you were comfortable with that, that's wonderful. If you would feel more comfortable showing a little bit of work, we can do that now. So what some people like to do with these is they like to say, okay, this point is -3, 3, and I'm going to keep the x the same and multiply by whatever number we were multiplying the function by. This point was 1, 0, so we're going to keep the x the same and multiply the y coordinate by 2. And this point is 2, 1, 2, -3. So that's going to become 2, -6 because the x stays the same. We multiply the y by whatever the number value for the vertical stretch or shrink is. And then this point was 3, -2. So when you do the vertical stretch, the 3 stays the same. We multiply the y value by 2 to get -4. So same graph results. The next one, I've called this function h, and this has 2 transformations. We're going to reflect over the x-axis, and we're going to do a vertical shift up 3. Now, for Algebra 2, whenever the order mattered for the transformations, I let you know. Here it matters. What we need to do is we need to do the reflection before we do the vertical shift. Okay, so I'm going to write a little hint here. Do the reflection before the vertical shift. Next year, when you're in pre-calculus, you will learn more about these transformations, and you will learn a sequence of transformations to use. All right, but for this year, I told you when the order mattered. So you want to do your reflection first and then your vertical shift up 3. So let's go ahead and reflect. And some of you can do this all at once without showing an in-between step. That's awesome. I'm going to show an in-between step. So I'm going to reflect this first. So 1 unit below becomes 1 unit above. This point is 2 units below the x-axis, so its mirror image is 2 units above. This point's 1 unit below, so its mirror image is 1 unit above. And I'm going to make this dashed because it's not my final graph. It's an intermediate step. And now I'm going to take that and I'm going to move it up 3. So I'm going to count 1, 2, 3 from there. 1, 2, 3. 1, 2, 3. So hopefully this topic is coming back to you pretty nicely. And if that's the case, you're going to be in really good shape for pre-calc next year. All right. Now, the next part of transformations to review is going to be with some common functions, because all those I just kind of made up the graphs, but we do also need to know some transformations of some common special functions, sometimes called parent functions. So absolute value graph is one you should know. That's your V-shaped graph, vertex at the origin, goes straight through quadrant 1, straight through quadrant 2. Your basic parabola, you should know, x squared. X cubed was new this year. Goes like this, right? I was always doing this in class. Okay. So x cubed goes up to the right and down to the left. And it is actually steeper than x squared, but it's okay if you don't show that exact steepness. And then square root graph has an endpoint at 0, 0, goes up to the right. The cube root graph, it was the inverse of x cubed, if you recall. And it goes up to the right, not steep at all. It's even less steep than square root, and down to the left like this. And then I included y equals 2 to the x. I know we also graphed 3 to the x and 4 to the x and e to the x and so on, but I just picked 2 to the x because you just want to be aware of the shape of that exponential function as you go into next year's class. I didn't include logs here because logs, you're going to relearn everything with logs in Precalc. Okay, so it'll be easier the second time around, but we don't expect you to walk into Precalc remembering how to do logs or how to graph logs. The exponential should be more familiar to you because you learned that in Algebra 1 also. All right, and I just picked 2 to the x for our basic one here. And let's go ahead and try some work with these common functions. So here's my first one. We're going to sketch the graphs and then give the domain and range as well, because that's another thing you need to be aware of for next year. You're certainly you can ask questions in pre-calculus class. So if you forget what one of these graphs look like, you can ask, but we do expect you to be pretty familiar with them in the pre-calc class. So looking at this example, I have absolute value x plus 3. So the common function I'm starting with is absolute value of x. And what we want to do with that is move it up 3. Because that plus 3 is outside. So when we did this year, I actually had you guys do a lot of point plotting. So I would actually have you graph y equals absolute value of x by plotting 1, 1, 2, 2, 3, 3, 4, 4, negative 1, 1, negative 2, 2, negative 3, 3, and so on. When you're in pre-calc next year, we actually just sketch them more often. So you probably won't be making very many tables for these graphs. So see if we can practice it that way today. So can you sketch absolute value x? Sure. I'm going to make it dash because it's not my final graph. And now, even though we didn't plot specifically 1, 1, 2, 2, 3, 3 on graph paper, since you know you're going to move this up 3, can you picture taking that entire graph and moving it up 3? The vertex will go from 0, 0 up to 0, 3. And then the rest of the graph will move along with it. So when you go to sketch this, try to make kind of like a parallel graph. It should look like you took that graph and moved the entire thing up 3 units. So there's nothing wrong with doing the point plotting and making the tables. But next year when you're in calculus, we aren't always looking at all the exact points. We're often more interested in the characteristics of the graph. So what we're going to spend more time talking about in pre-calc next year is the fact that this part's increasing, the fact that this part's decreasing, as well as the domain and range. So the domain for this one, since it goes left forever and right forever and there's no gaps in it, the domain's all real numbers. And the range we can get from the graph. The lowest y value we need to make the graph is 3, because I'm talking about the solid graph. Okay, so that's the lowest y we need, and we need all the y's going up forever. So that's your domain and your range. Okay, here's our next one. Of the 6 functions that I've given you choices of, when you see square root, what you want to try to do is think of the square root graph. This one was new this year. So this is one that you might not know quite as well next year. These you should know very, very well when you walk into pre-calc. But these guys are newer, so these you might need a little more practice when you see them next year. Okay? But this is our square root graph. So that's our common function. Some teachers call it a parent function. And the -4 is a horizontal shift. That's going to move the graph 4 to the right. So let's try that where we sketch instead of plotting all the points, because that's more what you're going to do in pre-calc. So the endpoint for the square root graph is 0, 0, and it goes up to the right, not very steep. So does that kind of look like this graph, but I just made it dashed? Hopefully it looks pretty good. Okay. Now we want to take that graph and move it 4 to the right. So instead of an endpoint at 0, 0, we're going to move the endpoint to 4, 0, and then slide the rest of the graph with it. So try to maintain that same steepness as you go up to the right. And it won't be perfect. Mine's not perfect either, but that's going to be good enough for most of what you're going to do in pre-calculus, because what you're going to be interested in are the main characteristics. The fact that the endpoint is 4, 0, the fact that this goes up to the right forever. The domain starts at 4, including 4, and goes out to the right forever. And the range, the lowest y we need is 0, and it goes up forever. It doesn't go up nearly as fast as the absolute value graph or a quadratic function, but it goes up to the right forever unbounded. It's going to go up forever, up, up, up. There's no limit on how high it can go. And a few more like this. For number 7, we have the same instructions. Now, when you look at this one, you want to think, what is the common function we're dealing with? So if you look at that equation, do you notice that there's a cubed? So I don't see absolute value, I don't see squared, but I see a cubed. So this is the one we're working on. Okay, I don't see square root, I don't see cube root, I don't see an x in the exponent. So this is the one we're dealing with right now. So we want to take that graph, move it 2 to the left and down 5. So let's try that. Okay, and I know when you did this in class this year, you would have graph paper and we would plot the points 1, 1, we would plot the point 2, 8 for x cubed, right? So we would plot 1, 1 and 2, 8. We couldn't fit 327. We would plot 0, 0 and -1, -1. And we would plot -2, -8. And then we would move that graph left 2 and down 5. But what you're going to do more in pre-calc next year is be aware of the shape of x cubed, which was a new one this year. Again, it's not that you walk in next year and you remember all of this on day 1, but when you see this graph next year, hopefully it comes back to you. You say, oh yeah, I remember that one. You want to take the whole thing and move it left 2 and down 5. So if we take this point on the origin and move it left 2 and then down 5, can you from that point maintain the same steepness going up to the right and down to the left? I think you can. You're not going to be perfect with this. So as you do this, you're not going to get the perfect x-intercept and y-intercept, okay? But does it look like I took that dash graph and moved the whole thing left 2 and down 5? It looks pretty good. My x-intercept's probably not accurate. My y-intercept's probably not quite accurate, but it's a sketch. And what we're going to be able to tell from that sketch next year in pre-calc is that the graph goes up to the right forever. The end behavior is falls left, rises right. If we're talking increasing, decreasing, it's increasing on the entire domain, because for increasing, decreasing, we trace the graph from left to right. So it's always increasing, even though the end behavior is falls left. You'll be reviewing those things next year as well. So the domain for this is all real numbers. Even though it's really steep and it doesn't go to the right very fast, it does go to the right forever. And it goes to the left forever as well. And the range for this one is also all real numbers. It goes up forever and down forever. Okay, 2 more. Let's get this exponential function going. So this is a transformation of 2 to the x. Here's what 2 to the x looks like, and it has a horizontal asymptote along the x-axis. And then that +4 is going to move the entire graph up 4 units. And you know that it's going to move the asymptote as well. That's the kind of stuff you need to be aware of next year. So we're going to move 1, 2, 3, 4 for the asymptote. And then if you recall, the y-intercept is usually 1. So that's going to move up to 5. Your graph is going to come down toward the horizontal asymptote to the left, just like this, because all we're doing is taking this graph, this dashed graph, and moving it up 4. And then this part that goes up to the right is going to go up to the right. You want to try to maintain the same steepness. You're not going to be perfect. I'm not perfect either. I just made a little bit of a mess there. Was going to get some white out, but I'm going to leave it because it's just a sketch. From that sketch, can you tell what the horizontal asymptote is? Yes. Can you tell that the domain is all real numbers because it goes left forever and right forever? Yes. Can you tell what the range is? Yeah. The range, the lowest we need is 4, but not actually 4 because we don't hit the asymptote. So parentheses on that 4, and it goes up forever. And last one from this video, we're going to look at x squared. So we know that one well. And we're going to do a reflection over the x-axis. And we're going to do a horizontal shift right 3. So I'm going to take that graph. I'm going to flip it over the x-axis. Let me resketch it. Okay. And by the way, your sketch might be a little different than mine because we're not doing graph paper right now. We're not plotting. We're not plotting for y equals x squared. We're not plotting 1, 1 and 2, 4 and 3, 9. We're just sketching it. So your sketch may look wider than mine. Your sketch may look a little narrower than mine. Because I didn't give you graph paper, we're not necessarily looking at this in the same viewing window. So it is just a sketch. But for all those, the ones I'm just erasing as well, they all have the same vertex, right? They all go up to the right, curved like this. They all go up to the left, curved like this. So it's good enough for a sketch. So this time it doesn't matter which one we do, what order we do it in. You'll learn more about that sequence next year. But let's go ahead and move right 3 first. Okay. So we're going to move this guy right 3. So the vertex moves 3 to the right, and then I'm going to try to maintain the same steepness going up to the right, up to the left. You might hit the y-axis, even though I didn't. That's okay. It's a sketch. And then we want to reflect that over the x-axis. So when we flip over the x-axis, the point that's on the x-axis is going to stay where it is. This is going to have a mirror image coming down. This will have a mirror image coming down like that. And from that sketch, even though we're not on graph paper pointing individual plots, we have enough information to tell things about this graph, like where the vertex is. It's at 3, 0. The fact that it falls right and it falls left. We also can figure out the domain and range by looking at this picture. The domain is all real numbers. And the range, be careful, you always have to go from low to high when you're doing interval notation. So the lowest the graph goes is down forever, negative infinity. The highest the graph goes is 0. That's the highest y value that we need to make that graph. All right, so that's it for the first of your 5 review lessons. At this point, you can move on to the practice set. Thanks for watching.